That's okay. Welcome everyone to December 2025's COVES Community of Practice webinar. Today we are discussing inferential testing. Um, if you are here to learn how to do one or two tests with your COVES data, I've got good news. Google exists. You can use some of the information here and just kind of figure out how you need to apply it. If you want to understand some of the theoretical underpinnings and how we've been thinking about these data to make informed decisions, you're in the right spot. But we're going to get super nerdy and I'm going to go super quickly. As I mentioned before the recording started, I am very thankful to all of you who participated in our planning survey, and I hope you enjoyed the fun Coves Halloween logo. We did get about a 17% response rate, which is actually great. 45 responses is a lot for us. I'm assuming that the majority of people who filled out that survey are here based on their intention to attend, which means we might have a little bit of a skewed sample here. The folks who did the survey, probably the folks on the call, probably the folks who are excited about this type of topic. So don't let this information skew you, but it might be interesting for you to know that we have 267 individuals on our webinar invitation list. And based on these responses, where you can see that most people are kind of in the middle of their current skill set, maybe leaning towards the beginner side of the expert continuum, and maybe very interested, I'm going to treat you all like a statistics class where about half of you are here because you want to be, and half of you are here because you feel like you need to be. So that's the way I've kind of been thinking about this in my mind. And one of the other questions we asked beyond a lot of the open-ended feedback we collected in that survey was your software preference. Most of you are Excel users, a few of you are SPSS users, a few less are RStudio. We had some write-in responses for Qualtrics, for SAS. No one seemed to be a Jamovi user. We're going to touch on that later. And many of you were open to suggestions. I want to acknowledge that Excel is a very powerful software. It's not my preferred inferential testing software because you actually do need to be very knowledgeable about the formulas and the tests themselves. You have to reconstruct things automatically, whereas some of the other systems that we'll talk about do things for you, and you need to focus on your interpretation skills. So that's where we're going to get towards the end of today. And as I mentioned again, here's the disclaimer. The stuff we're going to cover could be a weeks or months long process if you were to take a stats course, intro or intermediate statistics, undergraduate, graduate, wherever, community college, professional learning. And we're going to go through it very quickly. So please be aware that I'm going to skip 99% of the stuff that you also would learn in those courses. And we're just going to focus on some either true basics or some really important concepts that kind of build the foundation for what we're trying to understand in our testing and, of course, in our COVES data. So I thought I had this fun warm-up question. If you had to choose an answer at random from this set of four, what is the probability that you will be correct? And I guess I can't see the chat, and everyone appropriately went off video, so that's great. But I'll just break this down. If you chose A or D, the 25% response options, then the correct answer is 50%. But if you chose 50%, then the correct answer is 25%. But if you chose 0%, then at least you'd be right there. So it'd be 25% again. So the probability is actually zero, which is in itself a logical inconsistency. I like to use this example because all of the stuff we're going to talk about today is about probabilities, right? What is the probability that our sample captured the true information from the audiences that we're looking to learn about? What is the probability that our tests are able to discern differences that we're looking for, or maybe that we're not looking for because we want groups to be the same for one or more reasons? So, just kind of priming your brain to think about probabilities as we get into this statistical side of COVES. So there's five big things I want to talk about today, again, very quickly. We're going to go over some terms and definitions that set the stage for why are we doing this thing called statistical testing or inferential testing. We're going to talk briefly about statistical power and effect sizes, even though we're not actually going to calculate power or effect sizes, but I want you to be aware of why that matters. We're going to look at types of data and various tests generically, meaning like in the statistical inferential testing world. And then we're going to look at two specific examples from COVES data with some recommendations for how you can continue to apply this to a lot more of your COVES data. And then I'm going to end with complications, which I love to do because doing this in practice is not as simple as saying, like, I know how to run a t-test and here is the answer. You need to really be able to explain why it matters and the considerations that go into place before taking anything away from the tests. So I'm going to actually go through this whole thing and then I'm going to complicate things for you at the end just to, make this a fun hour. All right, so why are we doing statistical testing? If you are here, I am the stick figure on the left here who gets really excited about this type of topic. And I hope I can at least bring you some levity in the next 45 minutes around this topic too. But before I do that, let's get very basic. So there are some terms that are important to know. Most of you, many of you, all of you are familiar with them, but applying them in this setting might be new. So measurement, the assignment of some of numbers to some attribute, right? And then the scale is the assignment of rules to measurement. Overall experience rating is a good one. The scale is poor, fair, good, excellent, outstanding. The measurement is the experience rating itself. The variable then is OER in our data set. Variables can be classified into nominal, ordinal, interval, and ratio. I'm going to go over those in the next slide. And they depend on the scale of measure. There's two important pieces here, though, the descriptive and the inferential thing. Many of you in the pre-planning survey mentioned moving beyond descriptive statistics, right? Descriptive statistics are the frequencies, the averages, all of the pieces that you use to describe your COVES sample. That's great. The inferential statistics and the inferential testing that we're talking about today is how we move from that sample of data to the larger population. Most of the time, we think about our entire visiting audience. Not all the time, right? But that's generally who we're trying to make inferences about. That is the population of reference that we're really interested in learning about through our sampling procedure. Those variables that I mentioned, nominal, ordinal, interval, and ratio, they do go in that order. Nominal is the most basic. We can think of that like buckets. The software preference question that you answered on the planning survey is an example. SPSS is not greater than or less than or higher or lower on a scale than Excel. It's just a different bucket that you were able to select. Gender identity is also one of these. Regardless of how many categories they are, you can be in one, you can be in many, but they're not ordered in any way. An ordinal scale takes us a step beyond nominal, and it puts those in some kind of rank order, right? OER is a good example. Poor, fair, good, excellent, outstanding. The difference between poor and fair might not be even, but the order matters and they're buckets. Interval takes that a step farther and says that the distance between those response options is the same, right? So this is a bad example. Poor to fair and fair to good is the same distance. That's a bad example. A better example is 0 to 10 ratings, right? 0 to 1, 1 to 2, 2 to 3 are all even intervals. So the distance is the same between those response options. However, the difference between interval and ratio is the 0 on that scale, the NPS scale or the 0 to 10 rating scale, doesn't mean it's the absence of something. It means it's my least likely, my least preferred, the bottom of this interval list. A ratio scale has a meaningful 0 like the number of visits. I've never visited before, 0, right? Or my age is 0. Now, I know we couldn't sample people if they had not yet been born or if they had never visited, but you understand the concept that 4 is twice as many as 2, both in age or the number of visits. So those are some examples of ratio scales. Now, for populations and samples, the population, as I already mentioned, is indefinitely or perhaps infinitely large, and samples are subsets of that. The random sampling process is very important, and I'm going to talk about this again in 2 slides. But the random sample, as you know, comes from our data collection method when each member of the population has a known and independent chance of being included in the sample. And again, inferential testing comes from our opportunity to take advantage of the sample of data we have and apply it to the population. Many of you are familiar with these measures of central tendency, mode, median, and mean. If you haven't seen a slide like this in a while, remember that mode is the most common or the most frequent, the number that appears the most. As in the software preference thing, Excel was the mode, right? The most people chose Excel. Median is if you put everything in an ordered list, 50% of the cases will fall below that. It's often called the middle, but that does depend on the order and the style of measurement. And then the mean is, of course, the arithmetic average. So it's the combination of all those divided by the total number of responses. Most of the time, when people talk about mean, median, and mode, they're thinking about a distribution that's like the thing on my left. It should be on your left too, right? Looking at this, the normal bell-shaped curve. This is actually a picture of the standard normal, where there are demarcations on the bottom for z-scores, one standard deviation above and below the mean, and the percent of the distribution that falls in each of those ranges. The problem with this, even though we rely on the normal distribution for a lot of testing, is that our data in the museum world tends not to be normal. People don't actually fall into this nice bell shaped. We get skewed distributions like this example on the right. And even though it's framed negatively because the tail goes to the negative or less positive side of the distribution, the majority of cases fall on that positive side, right? So the negative skew means most of the observations are at the high end. That is how our museum data fall. Most people like our experiences. Most people chose to come here and have a good time. That is more typical of any of the distributional patterns you will find in your COVES dataset, where the mode is the highest measure of central tendency, the mean is pulled lowest by that tail end, that negatively skewed aspect of the distribution, and the median, still being the thing in the middle, is in between the mean and the mode. So that will come into play when we talk about parametric and non-parametric testing. But why does this all matter in the concept of inferential testing, right? The title of today's webinar. Representative samples mean something probabilistic happened, right? Random sampling, like we do for COVES, where we use systematic random sampling. You either approach every other group across an invisible line or something like that. You have a system in place for the random sampling procedure, is one of many types of sampling that could occur, including stratified sampling and cluster sampling. But the point is, if you took multiple representative samples from the same population, if you took multiple COVES random samples from your visiting audience, your population of visitors, you would expect them to be similar, but they would not be identical. And this is just due to random sampling error. As long as it is not systematic, right? If you have not introduced systematic bias into that sampling procedure, that is okay. Having small differences between sufficiently large samples, if it is done representatively through our systematic random sampling, that is okay. And that is exactly where inferential testing comes into play, because we can then put forth hypotheses, test them, and evaluate them against certain criteria known as type 1 and type 2 error. So, common questions of a null hypothesis are, does a particular sample of observations belong to a hypothesized population? In other words, does this small sample I have match the larger thing as a whole? Now, often in order to test that, you need to know the parameters of the larger thing as the whole. You need to know the true values of the population you're interested in. We don't often have that, but we can use the COVES data, for example, in the demographics we collect, to test to known population parameters through the census, even though the census itself is only a sample, right? It's not truly a census. But we're not going to touch that now. The second null hypothesis that's most frequent is, do two sets of observations represent samples from identical populations or different populations? In other words, do these two pieces of my sample differ or are they the same? And that's what we're going to look at in our COVES examples in a few more slides. The table on the right there is very helpful in evaluating this. Do I accept the null hypothesis? Do I reject the null hypothesis? Is there a difference? Isn't there a difference? And the true but unknown population effect. We're going to talk about power in the bottom right-hand corner, which is the correct decision of finding a difference and rejecting the null hypothesis when there is a difference to be found. I put a lot of jokes in this slide deck. Some of them land, some of them don't. If you haven't looked at Research Wahlberg on Twitter, it's a slightly older account, but at the time it was genius. And you got to, like, even if you don't like Mark Wahlberg, which many of us don't, they're pretty funny for the stats-minded group here. But anyway, as that joke relates to, one of the things that determines power, again, the ability to find a difference when a true difference exists, has to do with your sample size. And the other two things that will influence your power are your type 1 error rate, which is alpha. And the simplest way of thinking about that is, when p is less than 0.05, 0.05 is the alpha level that we're comparing to try and be under. We're trying to minimize our error by finding probabilities that are less than that 0.05 threshold. The effect size I'm going to talk about on the next slide, but quite honestly, this is probably one of the harder concepts in this whole lightning reintroduction crash course to contemplate because it's both theoretical and realized depending on the sample of data. So again, statistical power is this idea that I can find a difference in the data when the difference exists in the population. And an effect size is the magnitude of that difference. So it's almost, in my brain, it's a little backwards to think about. A large difference is easy to spot. A small difference is hard to find. And the question is, what becomes most meaningful in evaluating what an effect size is, the magnitude of the difference that you need to determine or detect based on the sample of data. There are different effect size calculations depending on the inferential test or procedure that you run. Most people refer to the standardized effect size, which is just the difference between means divided by the standard deviation. Again, that's the standardized portion of this. And you can think about effect size in these kind of rough categories that go plus or minus the notes here on the slide. Roughly 0.2 is small, roughly 0.5 is medium, roughly 0.8 is large, right? Things in between 0.5 and 0.8 are marge. They're medium large, depending on which one they're closer to. Why does all of that matter? Why does power and potential error and the effect size matter? Well, in our COVES situation, if we were to apply inferential testing to the samples that we're collecting from our audiences, you can think about a couple different scenarios based on any one of those three criteria. One, if you don't collect enough data and your sample is sufficiently small, your analysis will be underpowered. And even if a true difference exists in whatever you're testing, two groups, two periods of time, sample to the population, you might fail to find a difference even if it truly exists, right? You just don't have enough data to test. So sample size matters. The power of your experiment matters. You could consider another example. A power trade-off would be to say, well, I don't have a huge sample size, but maybe I'll change my type 1 error rate and I'll allow 10% of my statistically significant findings to be incorrect. So you might see a difference when one does not exist. Now, type 1 error and type 2 error, there's a debate about which one is more egregious. But in this example, changing your error rate probably doesn't do you much more good if the outcome of your inference is really important. A third example is if a true or meaningful difference is sufficiently small, so again, the effect size there, if it's very small but meaningful, you might have an adequately powered experiment that still fails to detect it based on any number of factors. So all three of them together, your alpha or your type 1 error rate, the power of your experiment, and the effect size that you're looking for, all influence, or sorry, the sample size, all influence the power of your experiment and our ability to find differences between groups, between the sample and the population, et cetera, et cetera. Okay, so that was a quick crash course on power, sample size, and effects. Now we're going to get into types of data and types of tests. So as we talked about, nominal, ordinal, interval ratio, there are many different types of tests depending on if the things are categorical, like the nominal and ordinal section, or continuous, the interval and ratio section of those measures. The common inferential tests that I'm going to speak about today are the chi-square test. There's a goodness of fit test and a test of association. We're going to talk about test of association, which is difference between two groups with respect to a categorical variable. I'm also going to talk about the Mann-Whitney test, the Mann-Whitney-Wilcoxon test, which has to do with non-normally distributed continuous data. So again, thinking about those distributional patterns that I put up before, we don't really see the bell curve. We see a skewed distribution, so we need a non-parametric equivalent. And then many of you in the planning survey talked a lot about correlation. So correlation is the pattern with which two measures move together. Um, the key driver analysis on your dashboard is a correlational matrix. It examines net promoter score and several of the other 0 to 10 ratings to see if they move in the same direction. Can one predict another? A correlation is an example of a simple regression, a simple linear regression, in which one could predict another. If two things had a perfect correlation, they'd be repetitive measures. So the question is, can we understand correlation to try and do predictive analysis? And I will say here that predictive analysis is very complicated, and I'll have an example at the end of these slides to illustrate that. You will see here on this slide as well that the t-test one is not as bold as the others because we very rarely have normally distributed continuous data in our COVES samples. That means that if you're applying a t-test to evaluate two means, you might not be doing the data justice. It might be an error, whether intentional or not, on your part of just like trying to decipher if these two numbers matter. The COVES dashboard is a good example, not of a t-test, but of possibly an ill-placed average. The 0 to 10 ratings show an average, right? Staff helpfulness, 9.4. Cafe quality, 9.1. Is an average the best for non-normally distributed data? Probably not. A median might be better, but the medians also look boring when you get to a sufficiently large sample, and that's a descriptive statistics conversation, not an inferential statistics conversation, so we can have that another time as well. Okay, I'm going to go through the top two, chi-square and Mann-Whitney, before we jump into actual examples of how to do this with your COVES data. And I haven't been seeing the chat. So again, Allison or Mallory, do I need to slow down at all right now? Thumbs up. Sweet. Okay. So chi-square test of association. As I mentioned, there is a chi-square goodness of fit test that matches categorical distribution against known population parameters. Again, goodness of fit could be testing race and ethnicity in your COVE sample to your local area census data. That would be a good example of goodness of fit. Test of association is going to bring that to the next level where we're looking at some categorical data against another categorical variable. So it tests two categorical variables and asks if they're independent of one another in the population. Non-parametric means it doesn't assume normality for a distribution of percentages, race or ethnicity, overall experience rating, which you probably know by now is definitely not normally distributed in our data. So this test is a good one for those types of responses or variables. It performs unexpectedly for cell counts less than 5. We're going to see this in action when we get to our COVES data, and I will highlight it there. In order to avoid this problematic area of chi-square testing, you can collapse categories by, OER is a good example, and I'll show it later. You can combine poor, fair, and good into less than excellent. You don't have to do that, but that is one example of collapsing categories. It's also important to note that this is an omnibus test, so when you find statistical significance, you might not know where. You might say like, the chi-square test is statistically significant. What does that mean? And that's where you'd use standardized residuals to identify influential cells in the example. I'll also highlight that in the output. The Mann-Whitney-Wilcoxon, as you remember, is the non-parametric alternative to the independent means t-test. In other words, I've got a continuous rating. Let's take a 0 to 10, any one of the 0 to 10 ratings on the COVE survey that we know is not normally distributed, but we want to compare two groups within our sample, right? So we're going to test these two groups and to see if they're independent of one another. The non-RM there means non-repeated measures. If you have repeated measures of any kind, one observation from one group and then one observation from another, we don't have that in COVES, but a repeated measures example would not apply to the Mann-Whitney-Wilcoxon because then you just look for the difference between those two groups. Helpful to know here has a question mark because I actually don't know how helpful this is for you to know at all. It is another non-parametric test, and the test itself puts all the groups together, orders the data, ranks them, and then sums the ranks to compute the test statistic, just in case you were curious about that. Some people call it the Mann-Whitney U. Some people call it the Wilcoxon rank sum test or the signed ranks test. I am going to abbreviate it MWW just for consistency on these slides. And I will make these slides available for everyone after the call as well, so you can use them as a reference. Okay, so now we're going to get to examples. Um, I like this joke here. I'll give you a second to read it. If you've heard me present in places other than the community of practice before, you may have heard me say one of my favorite jokes or one of my favorite aspects of being a statistician is never having to say you're certain. I do feel like that helps me out when I make mistakes. So, for the examples that I'm about to show, I pulled a subset of data that includes weekends only over a 12-month period from an unnamed member site, the Museum of Science. The sample size was 752. You'll see some of that play out in the output. Nothing here is compromising or overly revealing about this, but I just wanted to be clear that this is real data that we're going to be looking at, and you can do this with your COVES data very easily. Going all the way back to the planning survey at the beginning, we talked about different software preferences. And here is my quick interpretation of the top three that we had on the screen. SPSS is expensive, the full stop. If you don't have access to it, you're not going to get access to it. You're not going to buy a license and then learn it unless you're taking a stats course or your institution has some kind of license or discount partnership. The nice thing about SPSS is it does have a graphical user interface, right? It's got menu options where you can select the tests and do everything without needing to be a coding expert. But it also has a syntax coding window in case you get good at it and you can save things and just rerun your analyses over time. R is free to use. It's available on the web, easy to download. RStudio is kind of a window control that allows people to plug in R and do a lot of what I just mentioned about SPSS. It does require a little bit more of a learning curve around the coding, but the Jamovi platform also runs R in the background and has the graphical user interface. So no one selected that as their preferred software, but maybe some of you R users could play around with it to see if that helps. If you're already a coding expert, there's no need to go to Jamovi, but if you're thinking about learning R, Jamovi may be a good entry point. And as we talked about a little bit at the beginning, Excel is ubiquitous because many people run Microsoft, and even if you have a Mac, you might have the Microsoft suite installed. So free question mark, because most people have it or can get it online. Um, and even if it is ubiquitous and most people know how to use it, I would argue that many of us don't know all that it can do. And I will raise my hand and say, I actually don't know all it can do. I know I can do some statistical tests in it, but I would really need to rely on ChatGPT or Google to remind myself how. So, some trade-offs in the softwares. Again, we're going to look at examples in SPSS and RStudio. Okay, so the variables that we're going to use in these examples are overall experience rating. I've mentioned that a couple times. 0 to 10, I picked staff helpfulness literally for no reason other than an example. And membership status, because membership is an easy one to assign into groups that is just dichotomous, right? You either are a member or you're not. And even if your organization asks a fancy version of membership, like I bought one today, I used to be a member, but I'm lapsed, right? We recode all of that into I'm an active member during my visit or I'm not. Ones and zeros. It's actually ones and twos. So if you do dummy coding and you get into regression analysis, you're going to want to pay attention to the coding. But again, that's not today's topic. Going back to overall experience rating, you can see I put a note here about coding matters. There are 5 categories in that rating itself. I mentioned one example of collapsing categories into less than excellent, excellent, and outstanding. You could even go farther than that and do less than excellent, and that should say E plus, not O plus, so excellent and above. This is a way to overcome low cell counts, particularly in that poor and fair observation cells, which you'll see in the data here. All right, so I'm going to start with the chi-square example where we are looking at the difference between members and non-members with respect to overall experience ratings. It does not matter which goes into the row and column aspect of select variables, but if you're using the menu option, and I'm not going to, I apologize, for SPSS users, I think you know how to do this. And again, it's on Google or YouTube. I can find office hours to show you, but this is the procedure by which you'd use the menus. You'd go to Analyze, you'd click Descriptive Statistics, you'd click Crosstabs, you'd select your variables into a row and a column, and it's going to produce a matrix, which I'll show you on the next slide. It is important for the chi-square testing that you specify in the crosstabs through the options that you want the chi-square statistic produced, and that you give yourself some percentages in the rows and columns and totals so you can kind of evaluate the highs and lows of the distribution. And assuming there's significance, which is not a given, you want to select standardized residuals just in case so you can fact check where a cell or two is influencing the overall results. So again, we're comparing the overall experience rating between members and non-members using SPSS. And here is an example of the syntax, right? The code that you could use. You could copy and paste this. You can screenshot this, but you don't have to because I'm going to give you the slides. You could use this exact thing in your SPSS software, and it would give you results like what you see here on the screen. Now, if it's small for you, I'm just going to explain what I see. On the left, we have the distribution. Members and non-members populate the rows going across, and overall experience rating are the columns: poor, fair, good, excellent, outstanding. The test result table is on the right. You can see the Pearson chi-squared test statistic itself, which in this case is 1.925, and the asymptotic significance two-sided value, which just means both ends of the distribution, at 0.75. That is the p-value, 0.75. So that is the number most people look to reference against their alpha, their type 1 error rate, and say, is this greater than or less than 0.05? In this case, it's greater than 0.05, so we are able to retain the null hypothesis and say there's no difference between members and non-members with respect to their overall experience rating. In this case, that's great. I'm able to demonstrate that if I like what I see as far as the overall distribution of OER, members and non-members are getting sort of an equitable experience, or at least that's one possible interpretation of this test result. Here is the same image, but from the RStudio frame, right? So you can see on the bottom the test results. At the very top, you see the quote-unquote syntax, the coding, where we applied the member category and the OER category to data frames within a table. There is the distribution itself and the test statistics, the identical test statistics from RStudio as we received in SPSS. Same sample of data. It's important to note that different software might give you slightly different numbers, but the results should be the same. As I mentioned earlier, chi-square can be susceptible to low cell counts. If you look at the unordered excellent, fair, good, outstanding, poor, right, which is not our OER scale in that order, but the column for poor shows counts of 3 and 0. The column for fair shows 7 and 1. So 3 of those many cells are less than 5, which is why you get this warning right here that says chi-squared approximation may be incorrect. So that is one of the reasons why it might be helpful to collapse cells. Now, I did collapse cells as a coding exercise in advance of this presentation, and I'm happy to tell you that even if you use less than excellent, excellent, and outstanding, it is still non-significant, and those groups are the same, members and non-members between OER. Okay, I'm moving pretty fast. I'm going to get through this next example, and then I'm going to take a breath before getting to the consideration section. So bear with me. Here is the Mann-Whitney-Wilcoxon in SPSS. If you were to use the menu options, you would go to Analyze again, non-parametric tests, and go to Independent Samples. And you would be able to customize your analysis through the 3 tabs at the top: Objectives, Fields, and Settings. If you're not looking at SPSS, you can, again, apply this when you get to your software. And this is what the output looks like along with the syntax. So you can, again, if you wanted to do this analysis, take the syntax right there and you compare members and non-members with respect to their staff helpfulness ratings. Here, the test statistic is 35,969.5, which is an arbitrary, meaningless number, except that it computes a p-value of 0.549. So again, we compare this to our alpha level of 0.05. This is greater than 0.05. We retain our null hypothesis, and we establish that members and non-members actually are the same with respect to their staff helpfulness ratings. For our RStudio users, here is the coding at the top and the test statistics and the p-value at the bottom. Again, the exact same numbers come from the exact same data. We're able to say that there's no difference between members and non-members with respect to staff helpfulness ratings. Okay, I'm gonna take a pause because we're doing okay on time. I've heard some people dropping off. How's the chat looking, Allison?
Good. There's a question. Can you touch on encountering ceiling effects with certain variables?
Yeah, so that is a good example and why the chi-square distribution is a good one. So I'm gonna go all the way back here, right? So this distributional pattern, and even when you saw that the test table itself in both SPSS and RStudio, it was the asymptotic significance level. Asymptotic means the distributional line, in theory, never touches that x-axis. Well, that's for continuous variables, right? For things with ceiling or floor effects, or for categorical variables, there is a stop, right? There's a bottom and a top to this distribution. And ceiling effects are likely to actually mirror this negatively skewed distribution right here. It is impossible for us to go above a 10 on a 0 to 10 rating, right? But we know that many people have positive experiences, so that is why a lot of our distributional patterns appear skewed. Now, if we were to measure staff helpfulness on a 0 to 1 billion numerical rating scale, there is a likelihood that we would stretch out the variance and produce a more normal distribution than what we see here. That is actually the theory behind the sliding, like if you, what's that called? The slider scale, right? Instead of seeing 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, please select a number. It's just that slider, and it's kind of arbitrary where you put it. And maybe there's some words, and maybe there's some numbers up top, but you can put it between the 4 and the 5 or the 9 and the 10, right? It creates more variance in there. So it tries to eliminate floor and ceiling effects, but the end result is the same. And I'm going to come back to this actually in my consideration section too about the sensitivity of measures that we use and why that plays a role in how we interpret our data. So that's a great question. I hope I answered it a little bit, but probably not sufficiently, so we can come back to it.
Other
Any other
than that,
questions?
it's comments about there are lots of resources online. Liz linked a real statistics for help with Excel statistics if you want to use that
Yeah,
one.
there you go. At one point in my life, I did know a lot of the formulas for doing the tests in Excel, but then you have to type them in the cells and organize the data a little bit more, and I'm lazy. So good for you. And I think there's a real possibility there. But I would argue if you're trying to learn inferential testing in Excel because you have Excel, you could also learn R by getting R, right? It's you're learning a new skill, or at least a different way of interpreting, analyzing, and interpreting your data. It's just a question of do you rely on something that's already installed on your machine, or do you try and pick something else? Because there are courses for R as well. And in fact, if I didn't plug it before, the Visitor Studies Association did partner with R for the Rest of Us. I know some people on this call have already taken that course and have recommended it to others. So again, there are options that are cost effective, and there are options that are free too that you can learn some of this stuff with. Okay, I'm going to plow through so that I can stop sharing this and actually engage in a little bit of a discussion. But I do have about 8 more slides, 5 more slides, somewhere in between there. Look at this graphic, and the reason that this is important is because if you've read a research publication or any kind of journal article recently, you may have seen asterisks by test results. You may have seen 1, 2, or 3 asterisks. You may have seen words like marginal significance. You may have seen creative ways of getting at what the test proved or didn't prove. In actuality, it's not proving anything. It's just indicating the likelihood of something. Again, going back to probability. So this is a way of saying like p-values might actually be hurting us more than they're helping us. So the only things I really highlighted in the test results from SPSS and RStudio were the test statistic and the p-value, because those are the things you look at first to see if you need to look anywhere else for what the data are telling you. So before you get right into inferential testing, there's a couple things I want you to think about in advance. I'm going to talk about numbers 1 and 2 on the slide just out loud, and then I've got some short examples to get into. So 1, what is your null hypothesis and why? If you say, I think these two things are different. I think NPS is different from last year to this year. Why? Did the experience change? Did the population change? Are you actually hoping to test it so that you can prove that there is no difference and that the experience is the same or the likelihood to recommend is the same? A lot of times when people get into inferential testing, they just test to see if there are differences anywhere and everywhere, right? But I think the better question is to say, I expect to see a difference. In fact, we did this example not too long ago at the Museum of Science. I expect to see a difference between seasonal visitors, the people who come between Memorial Day and Labor Day, the people who come between Labor Day and Thanksgiving, people who come between Thanksgiving and like one of those winter holidays, President's Days, and then President's Day and again, Memorial Day, right? Because of what we offer, because of why they come, because of all the different things. And we were able to use our data and say, actually, there are no differences. So in this case, inferential testing helped us a lot because we were able to articulate why we thought there would be a difference in what we wanted to investigate. I encourage you all to think carefully about why you would expect to see a difference before you just get into testing. The ordinal versus interval debate, and this actually gets into the ceiling effect question. So thank you to whoever posed that in the chat. Many times, and COVES is somewhat guilty of this, although we've worked really hard to not be guilty of this. In museum measurement, we use scales that are less sensitive than an ideal situation. Strongly agree to or strongly disagree to strongly agree is a great example, right? If I've got strongly disagree, somewhat disagree, neither disagree nor agree, somewhat agree, strongly agree, right? I get a 5-point scale. A lot of researchers will turn that into a numeric score. They will treat those 5 categories, instead of thinking about them as discrete buckets, they'll think about them as more of an interval scale 1, 2, 3, 4, 5. And then turn that into an average and then test the average, even if it's not normally distributed. And this word debate on the slide is a little misleading. It implies that there's a rationale for treating ordinal scales as interval, when in reality it's the easy but wrong thing to do. In COVES, our scales are either numbered or they're not, and we treat the data as such. So we don't have that problem, but in general, inferential testing is subject to this, which test should I use question, which is why I started the beginning of our slides with the types of data and the types of tests. And I actually have a slide that I'm not even going to show, but will be a reference for you all, and a flow chart of, based on the data, what test do I pick? Okay, let's talk about these last few considerations for you. Statistical significance versus practical significance. So imagine 2 scenarios. These are made up but real in practice. I just didn't have the opportunity to pull data to highlight them. So imagine 2 scenarios. The first one, we have 2 groups, and I'm looking at net promoter scores, but these 2 groups have small samples, right? Let's say this was taken from our fall data the last couple of months when visitation is low. So my survey sample is lower than I'd like, but the 2 groups look different. The difference between the net promoter scores is almost 8, which feels to me it's got to be big, right? 8 points, almost 8 points. But based on the small sample size and the net score, regardless of how you test it, it's not statistically significant in this example because the analysis itself is underpowered. I don't have enough data to actually demonstrate that these 2 numbers are different. It could simply be due to random error in the sampling. That's a bummer. Okay, now imagine another scenario where I'm looking at large chunks of data, right? 2 full 6 months periods. Maybe there are 2 summers where I did really good at data collection. And the net promoter score between these 2 groups are very close, right? The net promoter score difference is 0.2. And it's found to be statistically significantly different because my sample sizes are so large and because 0.2 is statistically meaningfully different. But depending on these 2 groups, I have a hard time articulating why that matters. Why does 0.2 of a net promoter score matter? And what can we do about it? right? So there's the difference between not practically significant, but like practical significance. How do I act on this thing if the test shows me that these two things are different? What is the actual implication for us in understanding our visitors or their experiences? So again, that question kind of relates to establish your null hypotheses before you go into testing. Net Promoter Score. This was the choose the test wisely thing, if you want to reference Indiana Jones and the Holy Grail. For Net Promoter Score, do you consider it a three category measure where we're analyzing the percentage of detractors, the percentage of passives, and the percentage of promoters, since that is the information we use to calculate the net score? Or do you consider it a 0 to 10 interval scale where there are 11 possible selections and we have more variance because there's more possibilities? You're not bucketed into three groups. So there's a little bit of a debate if you are a Net Promoter Score fan, and if you're not, you've just skipped this debate entirely. And I even had one person in COVES a number of years ago challenge me that we should remove passives because they're excluded from the net score calculation. Now, whichever camp you fall into, and that could be one of many. I hate NPS. I don't know which test to use. It's certainly three categories, etc. Just don't treat it as an average, right? Where we use a t-test because we know it's not normally distributed. And furthermore, the net score itself is a bastardization of this 0 to 100 scale because you know from the calculation, net promoter scores can range from negative 100 to positive 100. So even statistical transformations won't help. The answer to this, by the way, is do either the chi-square on the three category measure or the Mann-Whitney on the 11-point interval scale. I reran the same set of data for our net promoter score in that 12-month sample that we used to investigate OER and staff helpfulness. And even though this is very small, both tests produce the same result, showing that there's statistically significant differences in net promoter score between members and non-members. Now, this is probably not that surprising. Members are bought into your services, or in this case, the Museum of Science experience, and are therefore more likely to recommend. Different than the overall experience rating, reflecting on the experience they had in the building that day. So, another consideration for you. Okay, last 2 points, and I know we're getting close on time, and I do want to see your lovely faces. Um, the American Statistical Association a number of years ago issued a warning against simply relying on p is less than 0.05 to guide anything. Interpretation, publication, you name it. They wanted to usher us into this quote unquote post p is less than 0.05 era because that damages your ability to talk about why this matters, the practical significance, and it also cheapens what people choose to publish, report on, present on at conferences because they need to establish that this thing mattered, right? An intervention happened and it changed people's perceptions, or there are differences between groups, or our, racial uh, composition of visitors matches census, something like that, right? Like it shouldn't always be about statistical significance. And even the American Statistical Association was urging us not to rely solely on p-values. And the final thing I'm going to leave you with here is causality in non-experimental settings. So if we find a significant difference, can we attribute it to anything other than, oh my gosh, those two things are different? Huh, wow. Is membership causing net promoters to be different? No. There's attributes that lead people to be members or non-members that we can't measure, and membership is a proxy for it. So in this slide, you see a spurious correlation, and if you haven't looked up spurious correlations on the web, I highly encourage you to do it. There is absolutely no reason to believe that the consumption of mozzarella cheese predicts engineering associate's degrees, right? That is a spurious correlation. And yet, using more than 10 years of data in this example, the variance explained is higher than 90%, which is as good as you're ever going to do in a full linear regression. So be careful of what you attribute as causal versus what just happens to be in the data, right? Investigate your data with more thoroughness. All right, there are additional slides, but those are just for reference for you. And I'm going to leave you with this quote as we head into a very short time for discussion. So there's a lot of talking from me. Um, I want to say I'm happy to stay on the call afterwards and talk with anybody who like really wants to needle me about some of this stuff. And again, through all of your input leading into this webinar, Mallory and Allison and I have already talked about ideas we have for next year and how we can create different resources. We've talked about creating some like office hours for RStudio users or Excel users or SPSS users, so we can, just screen share and kind of get into the weeds. So we got lots of ideas, but I'd love to hear from you, either questions about this presentation or thoughts you have after being dumped on for 55 minutes.
Statistics are cool.
Statistics are cool. Thank you for the comment, Megan. I appreciate it. We'll see you soon. So, no comments are great too. I'll just go back to what I said at the very beginning of this. Like, an hour doesn't do this justice. We would spend an hour and a half just on power and effect sizes alone for one type of test if we were taking a stats course, right? We spend an hour just doing the menu options for chi-square and doing a couple of examples and interpreting the output. You don't do all of stats in 55 minutes, even though I made the poor decision to try. Okay, to help us all out, I'm going to end the recording so the folks online get that, and then we'll stick around. Oh, no, don't leave the meeting. Can do this.